Hello, my name is Michael Evans, and I'm going to talk about measuring and controlling bias for some Bayesian inferences and the relation to frequentist criteria. And this is joint work with Yang Guo of the University of Toronto. To understand what I'm going to talk about, I have to go back to the beginning. So we imagine there is a scientific context and there's questions concerning an object of inference that I'll denote by psi, capital Psi. And we have data that X that we believe contains evidence concerning answers to certain questions. For example, the estimation question, I want to quote an estimate of the true value of psi together with an assessment of its accuracy. And for the hypothesis assessment problem, I want to quote the evidence either in favor of or against some specified value, perhaps arising through some theory, together with an assessment of the strength of that evidence. So what I want is a theory that somehow based upon characterizing or measuring statistical evidence tells me how to answer these two questions. And that's really the topic of a book by myself in 2015 called Measuring Statistical Evidence Using Relative Belief in the CRC series. Now there's other literature concerned with trying to base a theory of inference on measuring evidence. And I've given some reference there. And also, that's in the statistical literature. There's also quite a bit on this in the philosophy of science literature where it goes by the name of confirmation theory. So I have to add ingredients. If I could answer those questions just based on the data alone, that would be wonderful, but it seems that's not possible, and so I need additional ingredients. And what characteristics do I want these ingredients to have? Well, first of all, I want the smallest number of ingredients possible so that I get valid measures of, or valid characterization of evidence. Secondly, and that's really what this talk is about, the paper is about, I want to be able to assess the bias in the ingredients that I've chosen. Bias in the sense of foregone conclusions, and I'll talk more about that later. Thirdly, I want all the ingredients to be falsifiable. I want to be able to say, based upon the data, whether or not these ingredients that have been chosen subjectively by me or by some other analysts, whether they make sense in light of the data collected, which, if collected properly, should be objective. There could be other criteria that we would want these ingredients to satisfy as well, but those three for sure. Now, there are two ingredients in what I'm going to use here, namely the sampling model, which is a collection of probability distributions, one of which is supposed to be the generator of the observed data. And secondly, and that's falsifiable, right, by model checking, and also the prior, which is a probability distribution, proper probability distribution on the parameter space. And also that's falsifiable in the sense that I can check for prior data conflict. Now, another ingredient here, which really isn't chosen, is what I call the difference that matters, and I'll denote it by delta. And what that means that if two values of psi, possible values of psi, differ by less than the value delta, then from the point of view of the application, they're equivalent. This is often implicit because we measure the data to some finite accuracy, and that typically means that we can only know psi up to a certain accuracy as well. This has cropped up before in the statistical context because people, going back to Boring in 1919, complained about the difference between scientific significance and statistical significance. So these ingredients, the model and the prior in particular, lead to a joint probability model for the model parameter theta and the data x. Now, given the ingredients and the data, I'm going to apply rules of inference to these components to derive my inferences. And I'm going to cast everything in the context of a single probability model because that's what I have now. And suppose I want to know the truth value of an event A, but I have observed the event C. This event C is true. Then there's three principles that I'm going to apply here. First is the principle of conditional probability, which says that beliefs about A are now expressed by the conditional probability of A given C. I've updated my beliefs. The second is what is known as the principle of evidence, and what that says is that if the conditional probability is greater than the initial probability, then I have evidence in favor of A being true. If it's less than, I've got evidence against A being true, and if they're equal, I don't have evidence one way or the other. The third thing I'll need is that sometimes I need to have a numerically measure evidence so that I can order them. It's not that I need to express evidence on some particular scale, but sometimes I need to order them, order the possible values. And for that, I'm going to use the relative belief ratio, which is the ratio of the conditional probability to the prior probability. Now, if the prior probability is 0, of course, that's not going to work, and that happens in certain statistical applications. So in those contexts, I'm going to define my relative belief ratio as being the limit of the posterior probability to the prior probability of a shrinking sequence of sets, shrinking down to psi. And that leads me to define the relative belief ratio in those contexts as the ratio of the posterior density to the prior density. So the inference problem, or the estimation problem, that's solved by picking out the value that has the most evidence as expressed by the relative belief ratio, and I'll call that the relative belief estimate. And I'll measure the accuracy of that estimate by quoting the plausible region. And the plausible region is the set of values which have evidence in their favor. So I look at the size of that plausible region, and perhaps I also compute the posterior probability. And that gives me some assessment of how accurate my estimate is. And it's worth noting here that the plausible region really only depends on the second principle. It doesn't depend on using the relative belief ratio. So if I use some other valid measure of evidence, valid in the sense that it agrees with the principle of evidence via some cutoff, then might get a different estimate, but the estimate will also lie inside the plausible region. Now for the hypothesis assessment problem, I've already got the relative belief ratio as the assessment of the evidence for or against the value psi naught. And then I'm going to measure the strength of that evidence by that posterior probability that I've quoted below, but I'm not going to talk about that here. So now what about bias? I'm going to assert that bias calculations are necessary as part of assessing the quality of a study. For example, if I'm going to test a hypothesis that psi is equal to psi naught, suppose I could show a priori the probability is almost 1 that you'll get bias against, you'll get evidence against. In that case, if I actually reported that I got evidence against, you wouldn't find it particularly believable. Not a good study. So I'm going to measure bias in the hypothesis testing problem by computing bias against. There's two biases. Bias against, what's the prior probability of getting evidence against the null when it's true? And bias in favor, what's the probability of not getting evidence against the null hypothesis when the null hypothesis is meaningfully false? For the estimation problem, I'm going to measure bias against by computing the probability, the prior probability, that the true value is not in the plausible region. And you'll note that 1 minus that is the coverage probability of the plausible region. And I'm going to refer to that as a confidence. In fact, it turns out to be a confidence in the case of the model parameter. And when it's a marginal parameter, it turns out to be something like a confidence in a random effects model. The bias in favor, that's going to be the probability that a meaningfully false value is not in the implausible region. The implausible region being here, the values for which we get evidence against. Bias against, typically there's a value that maximizes the bias against in a hypothesis testing problem. And then I know that the coverage probability of the plausible region is always bounded below by 1 minus that probability. And so we have a lower bound on the frequentist or coverage probability of the plausible region. For bias in favor, this is of course similar to the idea of measuring the accuracy of a confidence region via the probability of covering the false value. Now you can prove that both biases go to 0 with increasing amounts of data. And what that means is that before I collect the data, I can determine how much data I need to make the biases as small as I like, or equivalently make the coverage probability of the plausible region as large as I like. And so I can get these frequency properties, coverage probabilities, for example, for any prior. I don't have to search for a prior that will give me the coverage probabilities that I want. I choose my prior based upon elicitation, for example, and then make sure I've got enough data collected so that the coverage probability is what I want. In the paper, we prove various optimality properties in terms of bias for this method of characterizing evidence. And a final comment is if these bias assessments are held as being essential, then there's complementary roles for frequentism and Bayes. Bayes is concerned with deriving the actual inferences, whereas frequentism is concerned with determining the quality of those inferences. And I've summarized the steps here in how I believe a statistical analysis should be conducted, and more can be found on this in the paper on arXiv. Thanks very much.